A slide. All right. All right, 12:30. That's the worst time for a class, I will assume. Right? Hopefully you had some lunch. Mine was at 11 o'clock, eating some cookies. All right, so the course is Statistical Computing for Scientists and Engineers. This is the second time we offer this course. It's not an introductory course. In other ways, I am assuming either you know a little bit of probability and statistics, or you don't mind picking up what you need to know during the class. So everything that you will need, I will give you notes and I will partially cover it, but I understand if I try to cover things in 2 lectures that in some other setting you will need a whole semester, I'm not going to be able to do the best job possible, okay? The course is really not advanced, right? It is the first course in a series of what we hopefully plan to have like 4 courses starting this year. So it's not an advanced course, but certainly it contains maybe material that is covered here and there in 4 or 5 other courses. So the idea here is you take this course because you don't want to take 4 courses only to realize that you haven't learned enough to do your research. So I don't want you to give up once I give the first homework, because last year that's exactly what happened. So I give the first homework and then the whole class drops out. Okay? Because effectively, it doesn't speak very highly of you. For me, it's not going to hurt my feelings because my feelings are already hurt, in many other ways. Okay? The guidance I have given to the TAs, and I'm going to introduce them shortly, is to give you as much help as you need, and if it is required to give you actually the solutions the day the homework is due, to do so as well. I don't want anybody to drop the class, because even if you have the solutions and you read them, you will learn enough things to feel happy at the end of the semester. Okay, a little bit about technicalities here. The website is this. If you go under courses, you will see our course. For now, at least for today, I cut it and pasted the course content from last year. So I'm going to have to work and put the updated lecture from today, okay? But the course from last year is going to stay on another link, which means if you want to see what is coming and you want to see the lecture material, you can do that as well. All right. So we have 2 lectures, Tuesdays and Thursdays. I also reserved this timing on Friday that I actually requested to be an hour and 45 minutes, and it's only 45 minutes allocated. And the idea was to use this before the homeworks are due for discussion with the teaching assistants, but also to use the time when I am on travel and we miss lectures, okay? Hopefully we'll have a combination of those, of all of these things. So really I cannot tell you that the recitation is mandatory, because I know graduate students don't like a class that has 3 lectures. Okay, it's too much for you, not for me. Okay, so this is a very end-user class, right? We only have, I think, about 20 students, and we have 3 TAs. I was really hoping we would have a 4th one, because there was a volunteer from civil engineering that works in this area. He's actually a research professor, but somehow the last minute his advisor said, "No way, Jose." Okay? He thought he would be spending too much time in this class, so his advisor did not allow him to help us. So the teaching assistants, the good news are all 3 students took the course last year, and they all struggle, which means they really understand what is working and what is not. So either they will help everybody and myself, or we will struggle even more altogether. Okay, right? So let me introduce them. Nicholas is up there. Govinda is also next to him, and Navid is just in front. Okay, so we have 3 TAs. They will obviously share tasks, right? So at a given time, at office hours for the TAs, one of them is going to be there. So last year we had no office hours for the TAs. So now we're going to have 2 hours of office hours. So some of them will be working in preparing homeworks and homework solutions, but in principle you can contact any of them if you like during the semester for questions, okay? Regardless of who has prepared what. So you will not even know, for example, if Govinda has prepared the homework for next week, okay? Because it doesn't matter. Now what I'm going to do is when I go back, I'm going to put web links or email links under their names so you know how to contact them. So office hours for myself, I put 2 hours. But if anybody really wants to see me at any day, if you email me, I'm going to be there at the end of the day for anybody who has questions. So, and even with these office hours, I would recommend, just in case I'm out of town, send an email and say I'm going to be coming to your office hours today, 1 to 2, so that way I anticipate that you'll be there. So everything is going to be on the website of the course. The website has an enormous amount of information, not just the lecture material, but actually links to original references, to data, to software. And I know it's too much information for any of you to handle in one semester. Basically, you don't have time to go and look at every reference, but I want you to know what is there, because maybe tomorrow, when you have something to do related for your research, you know where to look, okay? And there are links to books, and some of these books are available electronically as well. And if you cannot find them electronically, you can come to my office and I will give you a Chinese copy. Didn't say anything. All right. So lecture slides, references, homework, etc. Now, there will be 6 homeworks, 60% grade, and there will be a final project, 40% of the grade. But this year, really, I don't want to hear anymore affiliating your project with some very complicated research topics just because that's what your research is. Because I've realized from last semester and from last year and every other similar course that I taught, when I try to encourage students to integrate their research, they usually abuse the system, and at the end of the day, we have nothing relevant to the course. So everybody complains, oh, too much material, and then for a project, they do something extremely complicated because it relates to their research, and they are wasting my time and the time of the class listening to them. So really, the way that I see this, I want the final project to be equivalent to sort of a homework. The only difference is that you select what that homework problem is going to be. And so you can pick up a reference related to the course, right? And say, you know what, I'm going to reproduce these results, and I'm going to compare with what these guys have done, and and educate the class on a topic that we did not cover. Now, if you really want to do something related with your research, I have no objections. I will discourage it, however. Okay? It sounds painful to say that, simply because all the data that I have, after all this statistics course, all the data point to the fact that everybody abuses freedoms given for the projects. Not to mention, even, for example, last year, about 30 to 40% of the students changed their project about the day before the projects were due. And you can ask questions, and others, and they will tell you they changed basically what the project was, because suddenly they said, oh, a project is due, and what they proposed, they couldn't accomplish, so they started looking around, cutting and pasting. If they find the presentation on the web, they say, that's my final project. Okay, that's not. All right, books. There are no books for this course or other courses we're going to offer in the sequence. However, the books that you see, if you're really serious about the subject of computational statistics and machine learning and the way it interfaces with your work, you really need to have access to these books, okay? At least I follow things from here and there. So The easiest book on, it's really not on statistics or machine learning, but it's the easiest read, a fantastic read I may say, is the book by Chris Bishop on pattern recognition and machine learning. Don't be confused by pattern recognition and things like that if those names there don't resonate. It's a fantastic read. You need to read it. It doesn't matter what, you know, if you're going to do a PhD, I think sort of a textbook like this should be a required book for everybody to read. It's like learning English. The only thing different here is whatever you have learned in mathematics, etc., you revisit it now and you learn that some of the things you were taught, the approaches were not maybe the right approaches for the objectives that we're going to set forward in this course. The second book is a more recent book on machine learning. It has about 2,000 typos. It's more up to date, but it's a little bit less Bayesian, right? But still, it's a book that I would strongly recommend, but not as a textbook. So the first one, really, you can read it on your own and you'll be happy. This, you really need to look at here and there and extract the information that you need. The third book is covers Monte Carlo methods, and it's basically the standard textbook for Monte Carlo methods in scientific computing. So I will extract about at least 3 chapters when we discuss Monte Carlo methods in the context of Bayesian analysis. The rest of the books are all sort of the Bibles in statistics, if you like, by Robert and Gelman, you know, Bayesian analysis. And the nice things with, for example, Monte Carlo statistical methods, this book is, you can find online 2,000 pages of the slides that go with the book. You can find all the software, and you can even find video lectures. So there's really, in this is an open community, right? There's no, you know, you get some blah blah on some professor's notes. There is no such a thing. Everything is out in the open, and so you have no excuse to say, oh, I did not know about that. Because whatever you want, you can Google it, and you will find whatever information, because the machine learning community is very open, okay? So I don't see, okay, here it is. So this other book on called The Bayesian Choice, I think it's like 200 pages, and it is written, I think, from you know, from a perspective maybe of, I don't know, ecology, because it has lots of examples, and biology and things like that. But it is really like 10 chapters, independent of each other, but each chapter takes you from A to Z. So if there is this sort of relates to your research, this is a fantastic read, 200 pages. Of course, 200 pages doesn't mean you need 200 minutes to read it. You may need, you know, 20 months, okay? So it's a heavy book, but it's really very nice, you know, introduction, if you like, to computational statistics. And finally, this last book by James, I strongly recommend it. It's sort of the most modern approach to probability and statistics in the context of science, okay? I mean, the claim basically of the whole book is that science without probability is not science, okay? And so you will find this extremely refreshing because it provides a unifying view of probability and statistics. So basically, he explains why one algorithm is directly applicable to 50 different fields by reinterpreting what the meaning of the variables and the objectives are. It is possible that lots of these books are available online in the Notre Dame library. So if you go, you may be able to find all of these books online. All right. So what's the course objective? To introduce statistical methods for the simulation of complex systems. Obviously, we're not going to have enough time to discuss applications, right? This is a course to cover the fundamentals. But keep in mind, I am not going to tell you anything unless I know it is relevant to physics, chemistry, biology, engineering. So we're not going to do math for math, okay? So things have to be relevant to the simulation of stochastic systems, and really I'm referring here to systems in the presence of uncertainties. And we're going to do this using a Bayesian analysis, and we will slowly discuss what that means. If If you take other course in statistics, you may hear other things, but the dominant way of doing statistics is Bayesian analysis, and that's what we will cover. So I am actually going to use the Bayesian paradigm to introduce sort of what are the main problems that you have to face in your research. Like, for example, if you have some data, you want to make some predictions, right? If you know what the temperature was today and yesterday, you would like to know what the weather is tomorrow. And so I'm going to tell you what type of calculations we need to do for that. And we will see these calculations to actually be implemented. You cannot do them by hand. Even though there are some beautiful results done by hand, you really have to use approximations. And the approximation that I want to introduce in this course is Monte Carlo methods. And I think I will give you a taste of approximate inference, but this will be the second course in the series that I will hopefully teach this coming spring. Okay? So Monte Carlo method would be the obvious way of doing things, but the most expensive, and then approximate inference will be a little bit more elaborate type of techniques, but very cheap to program. Okay? So the idea here is, if you take this course and the follow-up courses, effectively you will be able to apply these techniques to any area of research of interest to you. Okay? And I want literally, maybe if you take 2 or 3 of these courses, to immediately see an enormous impact in your own research. Okay? So what I want you, when I cover certain topics, right, you may start thinking, is this relevant at all? Does any of the problems that I see in ecology, in biology, in engineering looks like that? And then extrapolate. Because I'm not going to be able to do all the extrapolation for you this semester, but certainly the techniques will be very general. So obviously we're going to use Monte Carlo methods to work on handling basically in a Bayesian way uncertainties in complex systems. And we will see, for example, I see the word there, integration. A lot of the calculations in Bayesian analysis eventually you have to compute integrals. And these integrals are integrals in very high dimensions. So you can think of a problem that has many, many parameters, like 1,000 parameters. So you're going to have to do some integration in 1,000 dimensions. And that's not something you learn in mathematics, basically a statistical way of doing this. So we will discuss how these calculations are done with Monte Carlo. And I'm going to give you not a superficial understanding of Monte Carlo. We will actually do it sort of rigorously, so when you write papers, you know how to write them. It's not like, oh, I'm using Monte Carlo and here's the answer. That's not good for my class, right? You're going to have to learn exactly what the notation is, what the error is of your approximations. Do you use enough data for your approximation to be useful for the type of things you're interested? And we're going to do this in the context of both static problems, but also problems that there is dynamics, okay? Because most of the problems in science, they're basically dynamical systems. So we will bring these techniques basically to a level where you'll be ready to do research, because that will be the last time we will explicitly discuss Monte Carlo methods. So why Bayesian? Really, I don't need to explain, since I haven't even said what Bayesian is, right? That's not good. So we're going to be trying to do inference and predictions using data. And this data that we'll be using will be either observations or simulation data. Actually, in the second course, we will extensively try to discuss the development of surrogate models for complex systems using simulation data, and even then we will use a Bayesian approach to that. We're interested to quantify uncertainty. So, if you have a complex system and you try to do a prediction, you say the temperature tomorrow is going to be this, that's not good enough from statistical perspective. What we're going to do is we're going to say tomorrow the temperature is this, plus minus that, where the plus minus basically will be probabilistic bounds. Okay, so we're not only going to give you the interval plus minus, but the probability affiliated with different possible temperatures that we can see tomorrow. I don't really have to tell you, if you do computation today and you haven't put your hands and your brains on statistics, basically you're losing 99% of science today. Okay, I mean I can say that because I wasn't doing statistics all my life, but I changed. I had the luxury one time to say, you know what, I'm going to stop doing what I'm doing and I'm going to move in this new area because there's excitement. And I hope each of you sees that, or already you have seen this in the open literature, not in science, but in magazines, in looking on searching things on the computer, etc. So we're going to discuss again some general themes that are common in science and engineering, and all of them will be driven by data. And the data that you hear a lot these days about big data, right? Big data. I just came from a meeting where, in the panel discussion we had, the buzzword was small data. Small data. Why? Because everybody has killed to death big data. The problem now is, can you actually make decisions, inference, when you don't have too much information? I don't know if the answer is absolutely yes, but I can tell you one thing. If you have only few data, the only way you can do anything at all is the Bayesian way. That's as much as I can say, right? So, when certainly we're not going to bother to say we have a lot of data or small data, etc. We're going to work with any data we have, even if the data are corrupted, even if the data are missing. We don't have everything. This is what we have, and we need to do something, and we will try to do the best possible. Okay? Now, if you're trying to build science with limited data, obviously you need to guarantee some convergence, right? It's not like you use a few data, you get some garbage, and you say, here's the answer. You're going to have to convince me that if somehow you had more data, your error bars would be smaller, right? Your predictions would be better, because if that is not the case, obviously something is wrong with the type of analysis you do, okay? So obviously the more the data, the better, but so that may not come explicit in everything we do, but keep that in mind. All right, so we discussed about Bayesian and Bayesian, okay? So doing Bayesian analysis in the context of scientific computing, it is a new area. I mean, most of the statisticians write little programs to do little tasks, right? Here what we're really interested is to address complex problems, like climate change or something, or some environmental problem that requires basically in a deterministic setting, very large-scale computing, okay? And imagine if you try to do this with uncertainty modeling, what do? You take a computer code that takes a day to run, and you run it a million times? That's not good. Nobody will allow you that, right? So obviously we need to work on these ideas in a smart way. All right, I removed several topics from last year with the promise that the course would be less heavy than last year, but more or less this is what we hope to cover. Some introduction to probability statistics and information theory. So I can easily see someone taking 3 courses for these topics. We're going to cover it in a few lectures. All right, so if there is a rigorous course in probability or statistics or information theory, you have my blessing to take those courses, because you will benefit, but we don't have the luxury to cover everything. We will only cover what we need for the topics of interest. We discuss the key ingredients of Bayesian statistics. What's a prior distribution? What's the likelihood? What's posterior? What's a predictive distribution? We will present some standard problems for doing Bayesian inference. And I will, the standard problem that everybody does is regression, right? If I give you data X and Y, you train a model to fit, to fit in, I'm using traditional terms here, we're not going to be fitting anything, but we're going to compute some function basically that represents the data, so we can do predictions for any X to figure out what Y is and what is our uncertainties about these predictions. So we will do regression, classification, I will. I don't really know if we're going to do this in a heavy extent, because maybe this is part of the second course, but certainly I will bring ideas of model reduction in the course. Now, this Bayesian inference, you may have to do some problems by hand, but all the problems require implementations in the computer. Okay? Those we will mainly do them with Monte Carlo methods. So it doesn't matter if you're from electrical engineering and you work in robotics or in ecology, or you are interested to predict what the stock market is going to do tomorrow, etc. All these methods are sort of unifying methods, and so we will try to cover them. About computing, I know if you take courses in, I don't know, in certain departments, they tell you we do everything in R, we do everything in MATLAB. In my course, don't bother me with how you do your computing. Do it in any way possible, all right? Use whatever language from any country, anywhere in the world. I don't really care, okay? So if you want to use MATLAB, it's good. If you want to use R, it's good. If you want to use Python, it's good. If you want to use whatever, all right? Now, if I was you, I would use a language where there is a lot of statistical programming already somewhere out there. Okay, that's the case with MATLAB, that's the case with Python, etc. What we will do is when we give you solutions, the solutions we have the computer codes in MATLAB and Python. Okay, and if nothing else, at least for the TAs, that would be a way to verify that the two codes give the same answers. If they don't, we're in trouble. But if somebody wants to use something else, I don't mind, right? I don't want you to basically waste time to write C++, to fit in on something that you can extract directly from a MATLAB toolbox, for example. Okay, but again, we don't force you to use one language or another. We hope you know something about programming, and if not, talk to the TAs. Start reading, whatever you want to do with any programming language, and we take it from there. So we will discuss a little bit about dynamical systems and state space models. Also, how sparsity comes in Bayesian models. The idea of Bayesian model selection, again, all of these things, you can integrate them together, so we can do model selection, say for regression or classification. So you will see this in the lectures as well as in the homeworks. We will discuss this algorithm expectation maximization, and we'll do some examples on how it applies to mixed models. Of course, you can generalize this to many other things. And then after that, if there is any time, I'm going to give you only sort of some taste of approximate methods, variational methods. The rest we will cover them in the course in the spring. So again, this is how the course is going to look. You may say, well, there are not too many topics, but think about, I can point you to classes on Monte Carlo methods where they're a year-long classes. Okay, so we're going to try to cover this maybe in 5, 6, 7 lectures. So be prepared that somehow there will be way too much material. I don't want you to learn everything, right? I want you to get the taste of what Bayesian things are, what are the main problems, what are the challenges, what Monte Carlo does for you, and how are these things coming together. And use the notes and the lectures as a resource to do the homework. So if you want us to do the homework only, the homework will cover no more than, 30% of these topics, because I cannot give you 50 homeworks. So if you can make the homework to work and understand it, then you're in business. You know a lot. Even if you don't know the rest, 70% of the lecture notes, right? Because I trust that when the time comes and you need, you can go back to these notes and fill in the gaps and further understand. All right. Any questions of general nature? By the way, if you ask something, I need to be sure I repeat it, so remind me to repeat it because the microphone may not pick it up. Anything generic about the course structure? All right. Usually when I give the first lecture, I I mean, for many years now, I covered the whole course on the first lecture. I want to convince the students that there's really nothing there. And somehow I have noticed undergraduates love it, graduate students hate it. So I was thinking, should I give you the whole course in one lecture, just to convince you that at the end of the day, everything, you know, it's just a few formulas here and there, and the rest is algebra. But then I said, you know what, I may scare you, and then everybody drops the class and I'm in trouble. So we're not going to do this. All right, so lecture one. There is no such a thing as lecture one being elementary, you know, AX equals B, right? So I see my TAs escaping, so there were not students leaving the room, okay? All right, so even if the lecture looks elementary, I'm trying to throw some ideas just so you can start challenging yourselves, okay? So one advice about the lecture notes, don't print them. I mean, I don't want you to waste paper, right? Please don't print them. They're online, and actually, as you come up to me and you say there's a mistake here, this link doesn't work, I improve things as we go along, okay? But don't print them, just look at the computer. So they're not to be printed. All right, so if you don't have a fundamental book like an undergraduate book in probability, all right, this is like the textbook. This is from a course at MIT that I believe has like 2,000 students or 3,000 students every time it's being offered, okay? Which has made Professor Bertsekas a rich professor because he decided to have his own publishing company because the book is so popular, but it's a fantastic read, this book. So in other ways, you can read the whole book literally, I would say in one weekend. I mean, you can get the sense of the whole book in one weekend, okay? And he has all the slides, all the homeworks, everything is free available on his website as well, okay? And it's an undergraduate really book, but lots of first-year graduate students take it as well. All right, so some terminology on probability and right now. So there are two approaches, as I already mentioned about the Bayesian way. The other way is what's called the frequentist way. And the frequentist way really treats the concept of probability as frequencies of events. Like how often is this thing going to happen? That's not the approach we want to follow because a lot of events that we're interested to work with are not coming in frequencies, right? I mean, what does it mean, for example, when I ask you what is the probability of the temperature tomorrow to be 40 degrees Celsius, for example? Well, you're not going to run from now to tomorrow and see how the weather is going to look like. It's going to be whatever it's going to be. There's no such a thing as long-run frequencies of events. So we're not going to follow this frequency probability, and we're going to treat what's called the Bayesian probability effectively as the means to quantify our beliefs about some event, okay? So it's like, oh, I believe that tomorrow is going to rain with probability 60%. That doesn't require frequencies, okay? It is an expression of our beliefs for an event, okay? So similarly here it says, the event that the polarized cup will melt by 2020, you cannot pose this in terms of frequencies. Now the good news, right? The mathematics of doing frequentist probability modeling and Bayesian probability modeling are the same, up to a point. But the fundamental rules basically that set how we're going to manipulate probabilities are basically the same if you do a frequentist approach or a Bayesian approach, okay? Now, back many, many years, right, everybody in statistics was a frequentist, and I think even the most, the people basically who were, had very strong animosity against Bayesian analysis, they have been converted now to Bayesian statisticians. You will have a hard time to find anybody who does really frequentist modeling, okay? Even a lot of medical journals now, if you do analysis in the frequentist setting, they will basically not accept your work, okay? Because there are some pathologies in the way the frequentist modeling. All right, so let me put all of these things up because they're very elementary. Okay, so I want you to just remember the essentials, right? And the rest you can read them when you go home. So we're gonna discuss first the sample space, which is, if you're gonna be doing an experiment, is the set of all possible outcomes of the experiment. So you can think, if you have a coin, the possible outcomes is heads or tails, for example. If you have a die roll, for example, the sample space is 1 to 6, okay? And an event is a subset of the sample space. So for example, for this case here, an event can be a set that contains only 5, or if you play with cards, the event that you get a face card consists of the elements J, Q, and K, okay? So sample space, all possible outcomes of the experiment, an event is a subset. So you can actually think of this really very much related, in principle identical to set theory that you learned in high school. So when you have, if you think of this using set theory, the way you learned, early on in mathematics, operations like the union of events make sense. So if you have an event that's 1 and 5 and another event that is 3, the union basically contains all the elements of phi and all the elements of f. All right, so the union of E and F is 1, 5, and 3. Okay, and similarly, the intersection, if you want the intersection of E and F, is the element 3 that belongs on both E and F. Okay, and now if the intersection is 0, okay, we denote this as you see here, and we call the two events to be mutually exclusive. All right, this is sort of important because it's going to come up often. Okay, 0 here is the empty set. Okay. All right, so you can extend this to literally infinite events, okay, and both for the union and intersection. And there are some mathematical issues that we're not interested on that have to do with this limit there. Laws of probability. The miracle of probability theory, right, is that it is based on a few trivial statements, and from those few trivial statements, miracles come out. So it's not like, you have to know about calculus and differentiation and integration and this and that and singularities. These are I'm going to put all of them up. This is the loss of probability. We're done. Okay? There is really nothing more. So we define the probability of an event, right? We denote this as the probability of the event E. And needs to satisfy the following properties. It has to be between 0 and 1, all right? The probability of omega is equal to 1. You remember omega is my sample space. So probability of omega means the probability that something is going to happen. Obviously it's 1 because something is going to happen. And the probability that, of the null set is 0 because obviously something is going to happen. And if you have events that they're mutually exclusive, okay, the probability of the union of these events is the sum of the individual probabilities. So again, when you look at this equation here, you should say it's mutually exclusive, okay? You can relate this to independent events that we will discuss later in this lecture, but these are the 3 laws, okay? I'm going to give you basically 2 more laws in algebraic form that are really sort of derived entities, but basically this is what we have, okay? And from these equations, believe it or not, you can do lots of fancy things. Okay? All right. By the way, lots of people in different communities, right, define probabilities their own way. People who work on interval analysis and this and that. And, the majority of the theories developed, they obey these laws. For us, this is what we're going to do, all right? So we're not going to stop doing weird things. We're going to base everything on these 3 laws of probability. So I don't really need to tell you all of these things. So let me just schematically, because I said that we are going to, you can use the analog of set theory, right? So if I have two events, E and F, that overlap, so they have some common elements, and you take the probability of the union, you can interpret that this probabilities is really represented with these circles. So this is the probability of F, this is the probability of E, and the probability or the union of E and F, you notice is the probability of F and the probability of E minus the probability of E and F, because you count it otherwise twice. You see that? If you want to find the probability of the union of E and F, right? Because these events are not disjoint, it's not equal to the probability of E and the probability of F. You have to subtract the probability of E and F because you otherwise count it twice. Okay. Let me introduce discrete variables, and I give you a schematic. So the idea here is we have a variable x that takes discrete values. So you can think that it can take the values, let's say 1, 2, 3, 4. Okay, this is the sample space. Before I denote this as omega, so this is a script x. So we define the probability of capital X equal to little x. So I need to take a step backwards here to clarify the notation. When you see capital X, in this case implies an event, let's say, or we will see in follow-up slides random variables. So X, you can think of the event, a little x is the value. So if this is, let's say, a variable capital X that can take the discrete values 1, 2, and 3, and 4, this little x is 1, 2, 3, or 4. So we denote capital X for the variable and little x for the values it can take. Okay? But lots of times you write this P of little x. Right? In papers, sort of, if you write something and you want to be rigorous, really this is the notation you need to use. So using the fundamental laws of probability, the probability of little x, so the probability that capital X will take that value has to be between 0 and 1. And if you sum all of these probabilities, it has to be equal to 1. This is, you remember, this is related to, where was my fundamental equation? To this equation here. The probability that something is going to happen, right, is equal to 1. Okay? All right? So effectively, the probabilities of P of X have to be normalized, right? And so let me show you one example. So here is capital X can take the values 1, 2, and 3, and 4, and I'm assigning here the same probability to all of these events. So you can see a graphical representation of this. Okay, so event capital X equal 1, 2, 3, and 4, and this is the corresponding probability. And here I give you a singular case where the sample space is 1, 2, 3, and 4, but I assign non-zero probability only to the value 1. And this function that we see here is what's called the indicator function. It's like a delta function, but we will use this indicator function in statistics. So the only probability we have is for X taking the value 1, and you can see obviously because these probabilities have to be normalized, this probability is equal to 1. Okay? So again, this gives you the concept of discrete random variables. Okay, the next two slides are extremely important actually. So let's be sure we understand them. I'm going to take two events, X and Y, or two random variables, X and Y, okay? And I'm going to assume that they are both discrete. So X can only take values Xi, and I put them here in a grid form. So X can be on this grid, or that value, or that value, etc. And Y can take these Yj values. So what I'm interested in is to discuss about the probability of the joint probability of x taking the values xi and y taking the values yj. Okay? Very elementary common sense calculation, but it will lead to a result that is extremely important for this course. So let's say that this is sort of a coin tossing experiment, right? And you repeat this experiment n times, okay? And you count how many times x will be xi and y will be yj, and the number that it comes is nij. Okay? So I repeat again, if this was coin tossing, right? You do one for x, one for y, you do the experiment n times, and you count how many times x will be xi and y will be yj, and that time comes to be nij. So obviously the probability of x being xi and y being yj is nij over n, using the frequentist way. We agree? Okay? So nij is the times in my n experiments, x will take the value xi, y the value yj. Now let me introduce the following. In this n experiments, let me call Ci the number of times that x is going to take the values xi. I don't say anything about y. Okay? So Ci is the number of times x is going to take the values xi. So let me do some simple algebra. So let's look at this equation. Don't put attention to the name yet. So look at this equation and look at the schematic and tell me if it makes at least some common sense to you. So what does the first statement, so this is the joint probability that x will be xi and y will be yj simultaneously. And what I see here, I see a summation on basically all the possible values of yj. So how do you understand this equation? I mean, this is the probability, the joint probability that x will take xi, y will take yj, and then I sum for all possible values of yj, which means it's like if you look here, all right, this is the probability that x will be xi, y, yj, and I say I'm going to take this value of y, and this value of y, and this value of y, and I'm going to sum all of this. So when you do that, what do you get? You will get the probability that x equals xi alone. You have marginalized, you have integrated y out. Okay? So this is what is called the sum rule of probability. It's basically marginalization. You take the probability of two events and you integrate one of the events out, and then you get back the probability only of x. This equation and the next equation are going to be coming literally in every lecture in this course and in every other course that I will be teaching at least. Okay? Very fundamental equation, right? And I do this for discrete variables. This is the marginalization. Okay? You integrate one variable out, and what you left is the probability only of x. Okay? So let me do a little bit more complicated now, another rule that's called the product rule. So we defined before the joint probability of x and y to take the values xi, yj as nij divided by the total number of experiments n. So what I'm going to do is I'm going to multiply and divide with ci. Remind me, what is ci? From the schematic, what is ci? The number of times? What is ci? That x equal to xi. All right. So I do nothing fancy. I multiply, divide by ci. So let's look first at ci divided by n. Can you tell me what is ci divided by the total number of experiments I've done? Is the probability of x being xi. Okay? And what is nij now divided by ci? That's a new entity. So now, if the way that I look at this, right, is like my whole space is not like the capital N experiments that I did before, but is the CI experiments. So here, by writing this ratio, I am looking at the case where x is fixed at what value? xi. And really I'm asking, how often is y going to take the value yj when x is already at the value xi? So really what this is the conditional probability of y given x. That's my definition actually of this conditional probability. So what you see here is the product rule, okay? If you have a joint probability of x and y, you can write this as the conditional of y given x times the probability of x. And from symmetry, I can write this as the probability of x given y times p of y. These rules of sum and product rule are the most amazing rules basically because from them you can get equations that are extremely complicated, but when you look at these two equations, the marginalization and the product rule, they look very simple, okay? I am doing this for discrete events, but you can generalize and we will see this as we go along. So again, the sum rule is you integrate one variable out, so you go from the joint to a marginal, and the product rule is basically writing the product, the joint distribution as a product of a conditional times here the probability of x. If I apply this product rule to many variables, so this notation implies x1 to x2 to xd, this will be a calculation that this product rule will give you, all right? Will give you p of x1 and p of x2 given x1 and x3 given x1, x2, etc. This will be an extremely complex calculation to do in practice, and somehow we will be looking to find ways to simplify the algebra that's involved in this formula. But really, if you look for the exact answer of writing this distribution, the joint probability of x1 to xd, this is the exact answer. It's computationally not very tractable, but we will see what we can do about it. Okay, so the sum rule and the product rule. I am writing now the sum and product rule for continuous variables. I won't give you any proof, Usually for me, if equations look reasonable, visually they look nice, they must be correct, okay? And if they're correct, then you should be able to prove them almost with no difficulty. So if you have continuous variables x and y, this is the sum rule, the marginalization, right? So the probability of x taking the value little x and y taking the value y, and integrating for all possible values of y, you get p of x. And then the product rule, you can write it like that. Okay? Exactly as if they were discrete, Things, the only difference again is the summation that we had here on y is now becoming an integral. All right, it's first lecture. I really need to throw you Bayes' rule, otherwise, this course is not going to be called Bayesian. Okay? So, let's concentrate on the equation on the top, right? If you understand that equation, we're in business, and you're not going to drop the class today. Okay? So, look at all the calculations and tell me how I go from the left to all the way to the right. So, what am I doing to go from here to there? So remember, there are only two rules. There's nothing else I'm going to introduce in the rest of the course. So what have I done in the first step? That's the product rule, right? It's just rewritten. The joint is the conditional times the marginal. Okay? All right. So let's look now in the numerator. What have I done? In the numerator, what calculation do you see? What rule is that? It's the product rule, but on reverse. You remember it's symmetric. I can do, condition of x given y or y given x. So this is really the condition of y given x times the marginal of x. On reverse. Okay? Now, on the denominator, what rule am I applying? In the denominator, you see I have the marginal of y, so what rule am I applying? I know the answer is hidden, it's there, so don't look at this equation at the bottom, okay? You're not allowed to look there. So how do I get the denominator looking like this? I mean, here is the proof, right? So we can look quietly. So to get this approximation, what's the first step I do? What's the rule? What rule is that? The sum rule. I say, let me use the marginal, all right? This is the probability of y, so I'm going to integrate x out, all right? So I'm going to sum for all possible values of x. And then what am I doing here? The product rule. And I use x prime, right, rather than x, because here the interest is the probability of x, capital X taking the value x. So I want to indicate x prime to be any arbitrary value of capital X, okay? So this is the sum rule, and then for the thing inside the summation, I am applying the product rule, and this is the nice thing I'm getting, okay? So so what you see actually on the top is everything that this course is about. We're basically done, okay? Because effectively, it tells you if you want to do inference of x given an observation y, you can actually reverse this and compute this entity on the left by using the probability of y given x times some prior information on x, and then normalizing, because really this is what this is, right? You can look, if you take the multiplication on the numerator, it's not going to give you value probability. So really what the denominator does, it takes whatever you had there and it normalizes it, okay? It normalizes it. So, so really, this is how you do inference. This is the Bayesian way. This is Bayes' rule, okay? And in this course, we're going to use this for discrete, for continuous events. We will use it all the time, but you have to trust me. There are only two rules in probability theory, the sum and the product rule. The rest is algebra. I mean, it's amazing. So, you know, you're going to tell me, oh, this course is too mathematical, it has too many equations. Really, it does not. It has only the sum and the product rule. There's nothing else. I mean, I remember some student came last year and says to me, Professor, this is not a machine learning class. It's a computational statistics class. And I look at her and say, yeah, because machine learning is really computational statistics. Isn't it? The machine learning that I know. All right. Let's do one example. Okay, this is from Bishop's machine learning book. So it's what time are we supposed to finish? 1:45. So I'm doing very good. All right. So let's consider very simple things. We have two. Let me see the names so I can see the acronyms. B is a box. Okay, so we have a red box and a blue box, and in each box we have balls that have different color. This is the orange, and what say? No, with you know I'm colorblind, so you have to help me here. Suppose a red and a blue box, all right? Red and a blue box, all right? Nice. Okay, so let's say we have this red and the blue box, and they contain these balls marked A here and O there. And what we're going to do is we're going to select randomly one of the boxes, and then from one of the boxes we're going to select a ball. Okay? And I'm going to tell you what the problem is, but before I solve this problem, I am going to assume that the probability of selecting the red box is 4 divided by 10, and the probability of selecting the blue box is 6 over 10. Right? They sum to 1, as you see. Okay? So 2 boxes. The first thing I'm going to do on my experiment, I'll say, oh, I'm going to take the blue box and then put my hand in and get a ball. Okay? So this is what I call the prior probabilities. Before I actually select the ball and see what color that ball has, these are the probabilities of me selecting the red box, and this is selecting the blue box. These are what we call the prior probabilities before we actually decide to select a particular ball. Okay, so what we do is we select randomly one of the box with these probabilities, and then put our hand in that box and we get a ball, and let's say it comes out to be an orange ball. Here's the problem. Considering that the ball that I selected was orange, all right, what's the probability that I selected it from the red box? So this is the posterior probability. Now I have some data, the fact that I selected an orange ball, and I'm asking what's the probability that that ball came from the red box? Make sense what the problem is? I'm going to try to apply basically Bayes' rule to see the previous equation in action for this problem, all right? So, okay, so let me, don't look on this particular equation. I'm going to apply the Bayes' rule, all right? And the Bayes' rule say, if I selected an orange ball, all right, what's the probability that the box was red? So I am writing this as the probability, what F stands for here? I mean, it stands for the ball, but why I denote it with F? Remind me, what does it say? There must be a reason, come on. Huh? Fruit, thank you. Orange and what's an apple? All right, thank you guys. Thank you. You see, I forgot to eat my apple for lunch, and that's why my brain doesn't function. All right, orange and apples. All right, so now I can discuss this clearly. All right, so the fruit was orange, and we're asking what's the probability that the box was red. So I'm reversing this with the Bayes' rule, all right? And what I get in the denominator, the probability that the fruit is orange, given that I selected it from the red box, times the prior probability that the box was the red box. Don't pay attention on the denominator yet. So look at this probability and says, if the box was the red box, what's the probability that the fruit will be orange? Obviously, 1, 2, 3, 4, 5, 6 is 6 divided by 8. Easy to compute when you know what box you are referring to, okay? And what's the probability that the box, the prior is the red box? It's 4/10, okay? And how do we compute the marginal now that the fruit is orange? And this should not be 0, should be a null, okay? So I need to collect it. So the probability that F is orange is a combination, remember, of the sum and the product rule. So it's really the probability that the fruit is orange given that the box was red times the probability of the box being red. And similarly, when the box is blue times the probability that the box is blue. These probabilities are all known. These are the prior probabilities. Once you know what the box is, for example, if the box is blue, and you say, what's the probability of this being an orange? So it's 1/4, so this comes 9/20. So you plug in, and the calculation basically, the posterior, that the box that you selected, the orange is red, is 2/3. And I am indicating here that this is greater than 1/2. So really, this is greater than the marginal of the probability that the box, the prior that the box was red. All right, so this has practical significance. And the significance here, it says, if you already have observed that the fruit is orange, you have already increased the probability that the box that you selected is red, because look, the orange box has way too many oranges. Right? So immediately, the fact that you collected this information, it changes your beliefs about what box you're actually selecting. Okay? So this probability here is way higher than the prior that we set it to 4/10. Let's do another example. All right? This is sort of a standard. I'm going to put this all up, considering our limited time here. So. I always, do this example when I go on trips to China, and I tell them, I arrive after a long flight, so I'm telling them I'm coming back from a trip, and I feel sick, which is 90% of the time, and the doctor thinks you might have contracted some disease, tuberculosis, let's say here, and 0.4% of the population has the disease. So the prior, basically, that someone has the disease is 0.004. Okay? And I call this the prior because I don't use any information. This is sort of average over the population. All right? This is the prior that you have the disease is 0.004. Okay. So there is a test that you can have to evaluate if you actually have the disease or not. But as you know, no test is perfect. Okay? So if you have the tuberculosis, the probability that the test will come to be basically positive is 80% of the time. Okay? So again, if you have the disease, the probability that this will come positive is 80% of the time. So immediately you're going to say, wow, if you take the test and it's positive, you are ruined. So we are going to have to investigate. You have to panic or not. Okay? Now, if you don't have the disease, sometimes the test comes positive. This is what they call false positive, and this probability is 0.1. Okay? So what we want to do is the following. I take the test, it comes positive. Should we worry? What do you think? So basically what I'm asking is, on this medical diagnosis problem is, if the test came positive, I'm asking you, do I have tuberculosis? Okay? So what you do is, you basically use exactly the same equation. You reverse basically the conditional here, all right? And then on the denominator you have to normalize, and you plug in all the numbers, and please, don't treat them as numbers. Look at the previous slide, what the numbers are, what they correspond. Be sure you understand. And you do the calculations, and it says here, the probability that you are sick, if the test is positive, is really very small. So you should not panic. And you know what is there in the calculation that actually makes this probability very small versus this number of 0.8 is the fact that only a very small percentage of the population has the disease. So it is the prior knowledge that somehow was sufficient to decrease the probability basically that you are sick. Okay. Now, just for the computer scientists in the room, and I know there's lots of them, right? We will do examples later in the course, and when we do classification and you have observations, you'll be asking, if you have, let's say, multiple classes, you can think, the data split in one Gaussian here, another Gaussian there, another Gaussian there. So you say, if I have an observation X, what's the probability that that X comes from that Gaussian? So effectively what this leads is to a classifier following this Bayes rule, where in essence, you're asking what class this point X belongs. C is a discrete label, can be Gaussian 1 or Gaussian 2 or Gaussian 3, all right? And you can see with Bayes' rule, to apply this, you need to have this class conditional probabilities. Basically, knowing in which class you are, you need to know what is the probability of generating X, okay? And that's why when you do classification, you apply the equation on the top. This is called a generative classifier, okay? It requires that you are able to generate data from each class C. Okay, again, I don't want to make you think that you need to understand everything here, but I want to just emphasize that the same equation we saw for Bayes' rule can be applied exactly as is to classification problems, where you're trying to assign labels to data, and you're asking what label should I put to data X? Well, if you have these probabilities, you can actually use Bayes' rule and do that quite easily. Of course, we will see all of these things in action slowly as we go through the course. All right, I have 6 minutes. So let me discuss some basic definitions of independence. So if we have two events A and B, we say that they're independent and we write them in this notation. The notation means sort of they're orthogonal, but really in probabilistic sense we talk about independence. So if the probability of A and B is, is the probability of A times the probability of B, then these two events are independent. That's very significant. Another way to write this is actually I don't want this. The conditional distribution, the conditional probability that we discussed in earlier slides can be written. You remember in the Bayesian, when we apply the product rule, effectively we wrote this as the probability of the joint of A and B divided the probability of B. If you take this and you plug it in the numerator, this is another alternative definition of the independence of two events A and B. So if you plug in here P of A times P of B and P of B cancel, you get that the conditional of A given B is equal to the probability of A. The idea here is simple. A and B are independent when knowing B doesn't give you any information about A. Okay? It sounds sort of not such a useful information, but trust me, in machine learning, it is conditional independence relations that will allow us to solve complex problems. Without them, we are ruined. The curse of dimensionality, too many variables. It is this sort of relations that will allow us to do efficient calculations. So what I define with conditional independence here is what I call a marginal independence. There's nothing conditional on anything, right? So the probability of x and y is the probability of x times the probability of y, but I can also write a conditional independence. I can say given z, x and y are independent. Extremely important equation. So this follows exactly what you see on the top. The only difference is I condition this on z. All right, nothing else. I have a nice example here, and I'm not going to do it because I want to discuss the next slide. So let me tell you what this slide says for, if you have many events, so in this case I have, let's say, 3 events. These events, if you take 2 of them, all right, together, they're independent. But if you take all 3 events together, they're not independent. So basically, for example, x1 and x2 are independent of each other, x1 and x3 are independent of each other, but but x1, x2, and x3 together, they are not independent. And I have this example because a typical mistake you can do when you have many variables is to test if they are pairwise, they're independent, and then you say, wow, they're all independent. No, they are not. Okay? Please follow this. There is nothing fancy, and if you have any questions, ask me. But I wanted to finish. If I have time, I'm going to come to this because this is very important. So we may do it, on Thursday. But I want to show you why independence relations are so crucial to doing efficient computing. Think that you have the joint probability of x and y, and take that x and y are discrete variables. All right. So let's say x takes 5 values and y takes, how many there are? 6. Okay. So in each of these boxes you can affiliate a probability. All right. So to describe this joint probability of x and y, where x takes 5 values and this takes 6 values, you know how many probabilities you need to specify? To fill this table, how many values do you need to put on that table? 30 minus 1. Why minus 1? Because the sum of all of these probabilities has to give you 1. All right? So it doesn't really matter on a big problem, 1 big deal, right? So let's, but for this case, to be precise, 29. Now let's assume that x and y are independent of each other, which means that the joint of probability of x and y is the probability of x times the probability of y. Now, how many values you need to describe p of x? 5, right? Because there are 6 values there, but they have the sum to 1, so it's really 5. And here you have 5 values, so you need 4. All right? So 5 and 4 is 9. So if somebody tells you, do you want to do calculations with something that takes 29 parameters or something that takes 9 parameters? Obviously, the choice would be 9 is good, because in a bigger problem, this can be 2,900,000 or something, and this can be 150. Okay? It is conditional independence relations that somehow allow us to solve complex problems in scientific applications. Okay? And actually, my course last semester explored this in the context of probabilistic graphical models. I don't have time to finish this, but if you can, go through the rest of the slides, and I'm going to come back on Wednesday. And this is sort of a very interesting application that has lots of implications. This example has to do with causal reasoning. All right? So I want you to look at it because it comes up certainly in biology, in complex systems, etc. Right? So we will pick up this example on Thursday. All right. So see you Thursday.
Professor, do you have a minute?
Please.
I'm going to be missing 2 weeks of class because I'm speaking at 2 conferences.
I'm going to be missing 3 weeks.
Oh my gosh. Okay.
Okay.
I just wanted to ask.
It's no problem because
Okay.
we will post everything on the web.
Okay.
All the videos, all the lectures, everything.
Awesome. Okay. But I just wanted to ask if I could audit the course.
I would like you not to.
Okay.